All right, good morning, everybody. Today, Form 4, we are going to continue with the physics section on forces, and we're going to look today at something called moments, or the moment of a force. Now, simply defined, the moment of a force is the turning effect of a force. Now, forces, as we know, can change the size, the shape, and the motion of an object. They can cause objects to move. So forces can also cause objects to have to turn, right? Forces can also create what we call a turning effect. So for example, you've experienced this a lot of times. When you open a door, for example, a door has two hinges, turning points. The door turns about that hinge. It pivots about that hinge. The hinge is the turning point. So when you apply a force and you pull the handle of the door, right, that force causes a turning effect and the door rotates or turns about the hinge, right? So that's an example of where you get a turning effect. For those of us who are around mechanical stuff, a spanner, for example, when you attach a spanner to, let's say, a nut, and you apply a force at the end of it, you get a turning effect about that nut, right? And that is what really the moment of a force is. It's the turning effect that you get when you apply that force on about, let's say, a turning point or a pivot. A common example of that is that of a seesaw. But before we get to that, how do you calculate the moment of a force? The moment of a force is force multiplied by the perpendicular distance, but very importantly, away from the pivot or the turning point. So it's the force multiplied by the distance away from the turning point. So I'll get to that in a little bit, right? And a unit, of course, since it's force multiplied by distance, right? The unit is the Newton meter. Newtons multiplied by meters, the Newton meter. All right? Now, if you were to look at this from a formula perspective, it would look like this. Force multiplied by L. L in this case is distance. There's no such thing as D, right? Distance is a length, and a length is a fundamental or basic quantity. So it's force by distance. A simple example of how we look at turning effect is that of a seesaw. So we've all been on a seesaw before, and a seesaw basically is a uniform plank. And from the time I say uniform plank, you should be thinking the center of gravity is, of course, directly in the center, right? And this triangle here represents the turning point or the pivot. So this seesaw is turning about this triangle thing here, right? Or turning about this pivot. Another word for the turning point is the pivot. It's pivoting about that point. Now, I have two weights here, 100 Newton on one side, and it's 2 meters away from the turning point, as you can see, 2 meters. And then I have a 200 Newton, which is 2 meters away from the turning point, right? So let's calculate, first of all, what the turning effect will be. Now, first of all, this 100 Newton force, if you were to think about this force, this weight pulling down like this, it will cause this entire system to rotate in an anti-clockwise manner. Whereas this force here, when it goes down this way, it causes this system to rotate in a clockwise manner. Okay? So we refer to the moment or the turning effect that you get from this force as an anti-clockwise moment because it's turning anti-clockwise. And this one is the clockwise moment because it's turning in a clockwise manner. So let's calculate. Force multiplied by distance, but not just distance. Notice the distance is a perpendicular distance, a right angle. That distance is a perpendicular distance. This force, 100 newtons, multiplied by the distance away from the pivot, 100 newtons multiplied by 2 meters gives us 200 Newton meters. On the other hand, we have a 200 Newton force here, and that force multiplied by that 1 meter perpendicular distance gives us a 200 Newton meter of clockwise moments, 200 Newton meters of turning effect. So in this case, right, these two